Hi. Just like with real numbers, we can add, subtract, multiply, and divide real numbers, we can also do the same with functions. In this presentation, we're going to talk about the algebra of functions, and we're also going to talk about a new operation called composition. So let's look at the objectives. First objective is we're going to use the operations on functions, evaluate composite functions, find the domains of composite functions, and find functions that form a given composite function. Let's start off with the operations on functions. Given two functions f and g, then for all values of x for which f of x and g of x are defined, f plus g of x is equal to f of x plus g of x, f minus g of x is equal to f of x minus g of x, f times g of x is equal to f of x times g of x, f divided by g of x is equal to f of x divided by g of x, and here we have to be careful and make sure g of x is not equal to 0. So let's try some examples. We're going to work with these two functions. We're going to let f of x equal x squared minus 4 and g of x equal the square root of x. We're asked to find f plus g of the number 9. We know by definition that that's equal to f of 9 plus g of 9. So let's calculate f of 9. So we get f of 9 is equal to 9 squared minus 4, which is 81 minus 4, which is 77. Now we calculate g of 9. G of 9 is equal to the square root of 9, which is 3. So that's equal to 77 plus 3, or 80. Notice that we can find the general addition sum of these two functions. We get f of x plus g of x, which is equal to x squared minus 4 plus the square root of x. In general, we have to be concerned about the domains of these functions. For functions f and g, the domains of f plus g, f minus g, and f times g include all real numbers in the intersection of the domains of f and g, while the domain of f divided by g includes those real numbers in the intersection of the domains of f and g for which g of x is not equal to 0. So let's look at an example. Let's let f of x equal x squared minus 4 and g of x equal the square root of x. Let's say we're asked to find the domain of f plus g of x. The domain of f is all real numbers. The domain of g is from 0 to infinity, including 0. So therefore, the domain of f plus g is the intersection of these two sets, which would be from 0 to infinity, including 0. Now let's try this problem. Same two functions, f of x equals x squared minus 4 and g of x equals the square root of x, and we're asked to find f minus g of 0. By definition, that's equal to f of 0 minus g of 0. We need to calculate f of 0. F of 0 is equal to 0 squared minus 4, which is negative 4. G of 0 is equal to the square root of 0, which is 0. So I get negative 4 minus 0, which is equal to negative 4. Again, we can find the difference of the two functions in general, and I would get x squared minus 4 minus the square root of x. Now let's try another problem. Suppose you're asked to find f times g of 1. Again, by definition, that's equal to f of 1 times g of 1. Calculating f of 1, we get 1 squared minus 4, which is 1 minus 4, which is negative 3. G of 1 is equal to the square root of 1, which is equal to 1. So I get negative 3 times 1, which is negative 3. To do the problem in general, if I'm asked to find f times g of x, I would multiply the two expressions, and I get x squared minus 4 times the square root of x. Finally, let's look at a division. Suppose you're asked to find f divided by g of 4. That's equal to f of 4 divided by g of 4. F of 4 is equal to 4 squared minus 4, which is 16 minus 4, which is 12. G of 4 is equal to the square root of 4, which is 2. So I get 12 divided by 2, which is equal to 6. Notice in general, we can also find f divided by g of x, and we get x squared minus 4 divided by the square root of x. Note here that x cannot equal 0. Now let's summarize our discussion about domains. Suppose we have f of x equal x squared minus 4 and g of x equals the square root of x. The domain of f is all real numbers. The domain of g was from 0 to infinity, including 0. The domains then of f plus g, f minus g, f times g are all from 0 to infinity, including 0. The domain of f divided by g is from 0 to infinity and not including 0, because that will make the denominator equal to 0. Let's look at another operation called composition. I'm going to introduce this by looking at an example. Let's let f of x equal 2 times x and g of x equal x minus 3. Let's find f of 5. F of 5 is equal to 2 times 5, which is 10. What I'm going to do now is take that result, 10, and put it in for the x in g of x. So g of 10 is 10 minus 3, which is 7. So g of 10 is equal to g of f of 5. Notice that notation. We can write that using what's called composition, which is an open circle. So we say g circle f of 5. A picture might help us visualize this process. Suppose we have a set x containing the element x. That is mapped into the element y of set y using function f. That in turn is mapped into element z of set z using the function g. We can write that as the composition of g circle f, and we'll call that h. So g circle f of x is equal to g of f of x, which is equal to h of x. Let's look at an example. Let's say we're given g of x is equal to 2x plus 1 and f of x is equal to x squared minus 3, and we're asked to find g circle f of 2. G circle f of 2, by definition, is equal to g of f of 2. We need to calculate f of 2 first. F of 2 is equal to 2 squared minus 3, which is 4 minus 3, which is 1. That now goes into our function g, so we need to calculate g of 1. G of 1 is equal to 2 times 1 plus 1, which is 2 plus 1, which is 3. In general, we can say that if f and g are functions, then the composite function of g and f is g circle f of x, which is equal to g of f of x, for all x in the domain of f, such that f of x is in the domain of g. In other words, all outputs of f must go in as inputs to g. Let's try another example. We're given a function f of x equals 3 divided by x to the 4th, and g of x is equal to 2 minus x. We're asked to find f circle g of x and g circle f of x. Let's start off by finding f circle g of x. Always use this notation. You have f of g of x, and that's equal to f of 2 minus x, which is equal to 3 divided by the quantity 2 minus x to the 4th power. Now, to find the domain of this composition, you have to look at the domain of the inside function, the domain of g. That was all real numbers. We have to recognize that the outputs of g of x are used as inputs to f. Now, we do have the restriction on f that x cannot be 0. So if we use the number 2 as an input to g, we will get 2 minus 2, which will give us 0, and that can't be used as the input to f. So the domain of f circle g is negative infinity to 2, or 2 to infinity. Now let's look at g circle f. G circle f of x is equal to g of f of x, which is equal to g of 3 divided by x to the 4th, which is equal to 2 minus 3 over x to the 4th, which is equal to 2x to the 4th minus 3 all over x to the 4th. Again, let's be careful with the domain. We look at the domain of the inside function, which is everything except 0, and we look and make sure that all the outputs of f of x can be used as inputs to g, and they can. So all we have to do is exclude 0. So the domain of g circle f is equal to negative infinity to 0, or 0 to infinity, not including 0. Okay, let's try this problem. Given f of x equals 1 all over x minus 3 and g of x is equal to the square root of x, find f circle g of x and g circle f of x and give the domains. Stop the tape and work on this. You should get f circle g of x is equal to 1 divided by the square root of x minus 3, where its domain is from 0 to 9, not including 9, but including 0, and from 9 to infinity. G circle f is equal to 1 divided by the square root of x minus 3, where that domain is from 3 to infinity, not including 3. Let's go through these problems. Here we have f of x is equal to 1 all over x minus 3, and g of x is equal to the square root of x. So f circle g of x is equal to f of g of x, which is equal to f of the square root of x. That's equal to 1 divided by the square root of x minus 3. Again, we have to consider the domain of this function. Now g of x was the first function that was applied. It has the domain x is greater than or equal to 0. If we look at the resulting function, we know that the square root of x minus 3 can't equal 0. So we have the square root of x can't equal 3, or x can't equal 9. So our final domain will be from 0 to 9, including 0, not including 9, or from 9 to infinity. Now we're going to try to find g circle f of x. That's equal to g of f of x, which is equal to g of 1 all over x minus 3, which is equal to the square root of 1 all over x minus 3, which is 1 all over the square root of x minus 3. Again, let's find the domain. This results in x minus 3 being greater than 0, x being greater than 3, so we have the domain of g circle f going from 3 to infinity, not including 3. Now we're going to try a different kind of problem. This is one where you're actually going to work composition backwards. We're going to be given that h of x is the square root of x squared minus 9. We're going to find functions f and g such that f circle g of x is equal to h of x. Now what I usually like to do with a problem like this is start off by thinking about the operations that are performed in this expression, the square root of x squared minus 9. When you're given a number and you substitute it in for x, the first thing that happens is you square that number. Then you subtract 9, then you take the square root. So keep these three operations in mind. So one possibility is to have a function, the inner function g of x, equal to x squared minus 9. It will take care of squaring the number and subtracting 9. Then the outer function must take the square root of that number. So I'm going to let f of x equal square root of x. Now let's check and see if that indeed does work. So we're going to take the composition f circle g of x, which is equal to f of g of x, which is equal to f of x squared minus 9, which is the square root of x squared minus 9. Is this the only answer? Well, it turns out no. I could have done the problem where I let g of x equal x squared. F of x then would be the square root of x minus 9. Let's check. So f circle g of x is equal to f of g of x, which is equal to f of x squared, which is the square root of x squared minus 9. So both answers are correct. All right, what we've looked at in this lesson is the algebra of functions and composition of functions. Pay particular attention to finding the domain of composition of functions. That can get a little confusing. We also had what is called going backwards in composition, finding two functions that when you compose them together give you a resulting function. That's also kind of an interesting kind of problem. See you next time.